On behalf of the Central Coast Amateur Radio Club, uh, 2020 Wyong Field Day Lectures, it's my pleasure to introduce Harry Chrysis for his exposition on his thesis work on parametric amplifiers and Bragg resonators. We know that amateur radio is an experimental hobby, and it'd be of great interest to us to hear some cutting-edge science. Thank you, Harry.
Cool. Well, thanks for coming. I guess, so a little bit about me. As I said, my name's Harry, and I'm just wrapping up my bachelor's degree at UNSW. So I'm studying electrical engineering and commerce. So that's what I've said, almost. And so last year I was working on my honours thesis, which was in the School of Quantum Computing, which UNSW is doing some really cutting-edge research on. And I guess a lot of it is actually, at the end of the day, some really, really clever microwave and radio frequency engineering and electronics. So I guess what I wanted to do was just show you some of the applications of RF electronics in the industry. I guess my caveat is all credit to the people whose papers I've drawn from, and there's a full reference list at the end. And yeah, just a huge thanks to UNSW for letting me partake in this. So I guess this is sort of, I guess the structure of what are we talking about? I guess what's the problem that I'm trying to address, or was trying to address in my thesis? Some of the current solutions that have been used in industry, the proposed solution that my thesis kind of involved in, and then towards the end, some of the contributions that I made. I'm not really sure what the level of expertise in the room is. I think there's quite a bit of variance. So I'm going to go for a fairly high level approach. And if you have any specific questions about some stuff I say, please just grab me. I'll hang around at the end. So the question is, what's the problem? And the problem is that quantum is small. So the whole field of quantum research comes by exploiting the power and the physics of the really, really tiny. So we're talking about the level of small numbers of atoms, or in some cases like single electrons or single photons. And so in something like a quantum computer, you actually store information instead of on a transistor, you can store it on an atom or like an electron. And it's amazing that we can do this, but this is cutting edge research. And there's some really cool experiments that you can do when you can actually take measurements at that length scale. So a really cool one is called electron spin resonance, which is a little bit like in an MRI machine, you can get atoms to vibrate and use that to image something. But if you can actually get the electrons as your imaging pixel, I guess, you can do things like take 3D photos of single cells and these kind of things, or you can do measurements on the length of nanometers, and you can do some pretty wild things. So needless to say, there's a lot of the issue comes from actually taking these measurements, which leads to quantum limited measurements. So this idea of how small can we actually measure? There's a limit to how small you can actually take a signal. When you get, and I know in all of RF electronics, you run into the issue of thermal noise. So basically the fact that if electronics aren't at 0 degrees Kelvin, if they're not really, really cold, the electrons and the atoms just bouncing around cause thermal noise, cause vibration, cause signals to be lost. And when you're dealing with single photons, even at liquid nitrogen temperatures, just the vibrations, just the thermal noise will just completely swamp your signal. And so the challenge becomes, how do you actually measure down to that quantum limit? Just as some napkin numbers, if you've got a 7.5 gigahertz photon, it's got an energy of 5, I think that's electron volts, but 5 times 10 to the negative 24 joules. And if you're at 1 degree Kelvin, so that's minus 273 degrees, so like 3 times colder than liquid nitrogen, your average atomic energy is about the same. So basically you need it really, really cold just for these signals to exist, which you can do. So this very cool thing on the left is that's what a quantum computer looks like these days. But you can do some really cool tricks by bathing it in liquid helium and just cool it down to 15 millikelvin. So you can get rid of the thermal noise, but you need some way of amplifying these signals that come out to above the next thermal stage, right? So you need some amplifier at this 15 millikelvin temperature that can boost the signal so that you can actually detect it at 4 Kelvin or 50 Kelvin. because it's not as trivial as just plugging in a coax cable or like attaching a USB cable, right? You really need to measure it. And this is where RF electronics comes in. This is where we can use the wonderful minds of microwave engineers to come up with it. So this is the kind of task I was working as part of, that the uni and I guess research has been given, is to design and simulate, build and test a quantum limited amplifier using a single layer manufacturing process. So what that means is by single layer, there's lots of structures where you can build them by like putting down a layer of material and etching away. It's very similar to PCB manufacturing, where you do a layer and etch and layer etch. But there's lots of advantages of being able to do it in a single layer. So you just put down one layer of, in this case, superconductor, but some conductor, and etching it away. One of which is the facilities at UNSW could do this. You can print an amplifier in 20 seconds. So this was kind of the task we were given. So what are some of the current solutions to actually use microwave electronics to amplify these incredibly tiny signals? As a bit of a theory tangent, a lot of them revolve around this process called three-wave mixing. And the idea is you can take your really small signal and you mix it with a pump signal that's about double the frequency, right? So if you're dealing with, a lot of the numbers I was dealing with was about 7.5 gigahertz. So if you have a roughly like a 15 gigahertz signal, you can use this process of three-wave mixing, where essentially what you do is your pump signal, this really large signal, which is shown in red, you can actually break the photons. You can break the signal into two photons, one of which is just some junk at the end called your idler, and one of which is the exact same frequency as your signal that you're trying to amplify. So essentially what you're doing is you're creating duplicates of this photon that you're trying to measure. And so you might have one in your signal, and through the power of parametric amplification, through the power of three-wave mixing, you can actually produce more and more. And that's just called amplification, right? Is creating a larger volume of the signal that you're trying to do. Yep.
That's a different signal.
Get a sum signal.
Yeah.
Yeah. Yeah. So there's kind of lots of ways to looking at it. So this is kind of the quantum way of thinking about it, of photon splitting. But when you look at it, if you just look at it at a spectrum analyzer, what you'd see is like, if you could really zoom in, you'd see your signal, right? And then you'd see your pump signal at double it. And you put it in this resonator, which I'll get to in a sec. And what you get out is all these harmonics. And you get sums and difference and 3 times and basically all these odd and even harmonics. But the critical thing is that your signal frequency actually gets boosted. And then what you do is you just chuck it through a low pass filter. You get rid of all the harmonics, and then you get an amplified signal. So the way they do this is through a process called parametric amplification, which is kind of the buzzword of this presentation. And what it means is if there's some parameter of your amplifier that you can modulate non-linearly, you can use this to amplify. So if you have a linear waveguide, right, that's just like think of a coax like an SMA cable. If you put in a 3 gigahertz signal and a 7 gigahertz signal, out the other end you're going to get a 3 gigahertz signal and a 7 gigahertz signal, right? It's linear. What you get in or what you get out is what you put in. If you have something non-linear about the signal or about the waveguide, you get exactly what we're talking about. You get these harmonics generated, and that's how you get this amplification process. So currently in industry, the way they make a waveguide non-linear is you need something non-linear, and they use these things called Josephson junctions, which are fancy quantum things, but critically, they've got a non-linear inductance. So for those of you who have done some basic electronics, inductance is just a feature of wave of any conductor that resists sudden changes in current. And a Josephson junction is this very small junction that has a non-linear inductance. So if you increase the current, the inductance of the joint actually changes. And so what it means is if you build a waveguide out of them, so this is what a thing looks like. These are just parasitic capacitances. But if you string together a whole bunch of these non-linear inductors, what you get is essentially a waveguide that is non-linear. And so this is kind of a way you can think about it where your signal comes in and it's incredibly small and you've got this large pump signal, and then over the length of the waveguide, you actually get this mixing happening where your pump signal gets decomposed into an idler, so this wave signal, but in the process it also amplifies your signal frequency. So this is really neat. There's a few issues with this. Lost track of where I'm. Yep. Actually, we'll go to this one first. And they've built these, and these things work. So this is kind of a bit of a setup. This is from a paper which is cited at the end of the slides. But the most important thing is this graph down here, and you can see they've used for a 7 gigahertz signal. They've used a pump signal that's about double that. And you can see over this really broad band, you get amplification. And you get issues when your signal is exactly half your pump frequency, and so that's why there's that dip in the middle. But critically, you can see over this quite broad band, you get amplification. Now, one of the issues, though, with these Josephson junction ones is these structures are very fine. So that's 200 nanometers, which is a human hair is 100,000 nanometers across. So that gives you a sense of the scale of these things. They're so small. And when you're trying to string together literally thousands, your yield is really small. So you try and manufacture a whole bunch of them. And if one fails short, you just have to chuck out the whole thing and start again. Another issue is that this is not a single layer method. So you basically have to lay down your first, because it's basically a capacitor, really. So you lay down your bottom layer, and then you put this like tiny oxide layer just by exposing it to air, and then you put down another layer. And that process is quite complex to line up layers and stuff. So they work, but they're real hard to make. So what's the proposed solution that the uni and this presentation is about? Is to use, instead of this nonlinear Josephson junction, you use another nonlinear inductance, which is this thing called kinetic inductance. Now, kinetic inductance is one of these things that's kind of blew my mind the first time I thought about it. So, as I said, as RF engineers or electrical engineers or hobbyists, you'd be quite familiar with inductance, which is, basically if you have a conductor and you try and force a change in current through it, your inductance will resist it. And if you actually go into the maths, the inductance is just a function of the geometry of your conductor, right? So if you have a longer conductor, your inductance will increase. And if you have a thicker conductor, it will decrease, I think. My lecturers will be appalled at me right now. But yeah, so it's a function of the geometry of your system. What they found, though, is if you get really, really small, so as I said, in the order of nanometers or microns, you get another inductance coming up, which is called kinetic inductance. And what it actually is when you get, these tiny wires, you actually find you can't suddenly just switch the current because the actual electrons carry momentum. So you've got the electrons traveling in one way, and then if you try and switch the current, they kind of resist that change because they have mass and because they've got some kinetic energy. And so this is called kinetic inductance. And so if you just grabbed a wire and measured the inductance, there's no way you'll measure it. This is in the order of picohenries. But when you get to these tiny, tiny structures on superconductors, on micron and nanometer scales, you actually can observe this thing. And the really important thing about this is kinetic inductance is actually nonlinear. And so you can use it for this parametric amplification. So this is just some napkin maths once again. I can't remember the exact dimensions we used, but basically for a really, really thin inductor, so I think this was a micron across, if you do your second year electronics calculations, the geometric inductance comes out at 0.4 nanohenries. But if you actually consider the kinetic inductance, it comes out at about 30. So the point being, the smaller your structure gets, the kinetic inductance actually becomes the dominant inductance in your conductor. It's literally kinetic energy. Yeah. Totally, yeah. Yeah. The way I think about it, it's kind of like, water hammering. So basically, if you've got water flowing in a pipe, you can't suddenly block the pipe. Well, you can, but you get this massive spike in pressure. It's very analogous to that, where you've got in a really bad way of thinking about it, a wire is just like a tube of electrons, right? All traveling in one direction. And if you try and switch that, there's resistance to that. If you're being really technical about it, this is actually a superconductor, so it's Cooper pairs, but it's pairs of electrons. Like it's all particles with mass moving at some speed. Yeah, so it's real neat. Oh, sorry, I just saw this. Yep, so this is a 250 nanometer by 1 millimeter strip of 20 nanometer niobium titanium nitride, which is just a superconductor. But yeah, real small. And so you can actually build a parametric amplifier out of this stuff. So what you do is you build, so this is a top-down view of just a coplanar waveguide. So I imagine as hobbyists, you'd be fairly familiar with this structure. All it is just a ground plane either side with two splits, and then you've got your semiconductor down the middle. It's basically just like a coax cable that you've sliced. And this is good enough for parametric amplification, right? It's non-linear, and so if you put a signal and if you put a pump signal in there, you're going to get amplification. It's really cool. Then what you do, and I'll get to why you do this in a sec, is you actually modulate the frequency or the width of the semiconductor. So you load it essentially. So you create these little regions of high capacitance, low inductance, and what it creates is this band, like essentially a notch filter, right? So you get these notches at integer multiples of how, like your periodicity of those bands. Then what you do is every third band you shrink, so you make the loading smaller. And so what you get, the point of all this, is you get this kind of band structure, right? Where you've got at every, so the last slide was not heaps correct, but this one's the correct one. At your low frequency, so this is now periodic with every third one, you get these band gaps, and then since you've modulated these thicker ones, every third harmonic you get these really big wells, right? So you get these notch filters and you get these really big ones in the third harmonics. And what you do is you line up your pump signal right at the edge of one of these. And so what it means is your pump signal gets out, but you filter out the third and the fifth and all the odd harmonics. So it's this quite neat way of you just get your fundamental frequency, but you lose your harmonics. And the reason you want to do that is for two things. One is over the length of your transmission line. So these things are actually quite long. As I said, they're like something like microns thick, but they're actually like 2 meters long or something. They just meander them really, really tightly because you need the length to actually get the mixing. Over the length of that, you actually get your signal and your pump. You get a dispersion between them. So they actually, as they head along, since they see different impedances, one will propagate at a different velocity. And so what you do is, the reason you load it is you create a frequency-dependent dispersion relationship. So basically, the way I kind of think about it is you've got your pump signal traveling down and your signal traveling down, and I guess one of them is propagating faster than the other one. And so what you do is you load it, so you kind of slow it down so they're in phase, and so you can actually get mixing happening. The other reason you do it is, and the reason you want to filter out your odd harmonics is to avoid this thing called shockwave generation, where basically if you let odd harmonics build up, the peak of your pulse that you sent down actually because since it's non-linear, since the electric field's strongest there, it actually sees a lower epsilon naught, and so it propagates faster, and so you get these shockwaves building up, which are really bad for these structures because you can get things shorting. Yeah, basically. There's lots of fun analogies you can use in the world of quantum. But yeah, so the point of this, and this is like an artist's impression one, but you meander this thing around. But this is one, I can't remember which group, this is from a paper by Vissers, so you can look that up. But this is a 2 centimeter by 2 centimeter chip, and they've got a 2 meter transmission line on there. So these, like, the scale on these things is just crazy. But yeah, and what you do is you cram this thing into a chip, and you put in the kind of goal of all of this is you put in your signal frequency, you put in your pump, and out the other end you get an amplified signal. and then yeah, you kind of it works. And these are some of the photos of just so credit to my supervisor. This is some test etches. So these things are made in real life and they work. This is sort of what the structure looks like. So you taper it down so you can get your 50 ohms because we don't like reflections. And yeah, you kind of meander it. And it doesn't really matter how you meander it. You can spiral it or you can use this kind of structure. So that's one solution, that's what you call a traveling wave parametric amplifier. So it's a traveling wave because it's a 2-port device. So you've got one in and it kind of comes out. The advantage of that is it's nice and it's clean and it's 2-port, so you don't have to worry about circulators or those sort of things. One of the difficulties is they get real big. So as I said, 2 centimeters by 2 centimeters doesn't sound large. But when you've got a quantum fridge where your workspace is tiny and your cooling power is like 50 microwatts or something, like you can, basically you need really small devices. So another thing you can use, and another structure we investigated, was something called a Bragg resonator. And basically how it works is instead of having your 2 signals mixing over the course of this really long waveguide, if you can kind of trap them in a resonant cavity and get them mixing for a long period of time, when they come out there's amplification and you can just feed them through a circulator, low pass filter them and you get your signal back. And the way these structures work is you've got what's called a Bragg mirror. So basically it's just N cells of like a low impedance section and a high impedance section. And so this is like 3 cells. So you've got this Bragg mirror structure, and then at the end of it, you've got either a grounded, well, I guess you're using inductance. So yeah, you've got a grounded quarter wave resonator. So the idea is you use this, the Bragg mirror to kind of increase the quality factor of this resonator here. So you're kind of trying to trap your 2 signals in there for as long as you can. And this is just briefly, this is how these Bragg mirrors work. Basically, you modulate the characteristic impedance every half wavelength, and so you get these reflections of interference patterns that basically cause this really high quality factor reflection. And so this is kind of the goal of this, and this is the simulation that I was running, where this is a Bragg mirror that's trying to reflect out or trying to filter out 7.2 gigahertz. And so you can see there's a really, really deep well, all right? There's a really good reflection of that frequency, but also for any signal that does manage to propagate into that resonator structure, there's a huge, huge quality factor, like a really, really good quality factor resonated there. So I guess the way you can kind of think about it is you've got this mirror structure that tries to block out 7.5 gigahertz, but the small amount of that actually can make it into the resonator will resonate over a long period of time, and so you get this real large amplification happening. And these totally work in practice. So you can see over 7.3 gigahertz. Over this band, you get a real, like, right at the middle frequency, you get this huge amplification of like 15, 16 decibels. As you can see, as opposed to the traveling wave one, this one's got a really, really narrow band of amplification. So you end up with a few different advantages and disadvantages. For a traveling wave one, you get a really nice broad band of measurements, but it's quite, it's quite large and quite difficult to build. And the Bragg resonators, it's a really small structure, so it's nice and efficient and really low energy, but you get a really narrow band of amplification. Another advantage is it's a smaller structure, and so there's less to go wrong. So when they actually build these things, you can end up with like stitching errors. So if your structure is 2 centimeters by 2 centimeters and you're etching it with an electron beam, you kind of pick a section, etch it, move it across, pick a section, etch it, and you do that. And at the boundaries between those etching regions, you can get these stitching errors. That'll also cause your device to fail. So another advantage of these resonant structures is you can basically put it in one right field and just go pink and just build the whole thing in one fell swoop. Yeah, so those are the kind of two structures, 2 options. As I said, there's lots of advantages to them. So first and foremost, they give you this amplification. So you get a broadband of amplification. And broadband's really good is because you can multiplex a whole bunch of qubits or signals or whatever through it. So if you have a nice broadband, you can amplify a whole bunch of frequencies at the same time. And you can also, since it's a grounded structure, you can actually DC bias it. So instead of having a signal around ground, around zero, you can bias it with an offset current. And that increases the amplification for reasons which I can explain to you later. It's much easier to manufacture these, the resonator structures. So you can build them both with a single layer process, which means they're quicker and there's less errors when you're actually during the etching process. Since they're smaller, they consume a lot less power, which is, it's not an issue in terms of efficiency, it's an issue in terms of cooling. So as I said, all these things have to happen in a really, 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 really cold fridge. And at those temperature scales, your cooling power is sort of like 15 microwatts. You compare that to like your kilowatt fridge, right? And so you need things that use so little power because you can't afford any heating, really. And lastly, they're really simple. So structurally, they're quite simple, and so you can develop them and draw them and etch them with a really high yield. And I think some test etches were taking like 20 seconds to build these things. So they're nice and quick. So that's a really, not a high level at all, quite a technical, but that's an overview of what the proposed solutions were. You're trying to do some quantum limited measurements. So you're basically trying to measure these single or multiple photon signals. And the way you do that is through parametric amplifiers, actually amplifying the signal through this wave mixing process. And there's two options you can do. There's that traveling wave structure where you've got a 2-port device, which are nice and broadband but quite cumbersome and large. Or there's a Bragg resonator, which is like a real small, nice and efficient one. So I guess the last thing I wanted to talk about is just where I kind of fit into this, sort of what an undergraduate electrical engineer can contribute to these sort of things. And so there's a couple of things I did. First thing, I built a box. So this is, it did get made, but this isn't a photo. This is just Fusion 360 and a graphics card. But this is kind of what the thing will look like. So I drew up this copper box, and it gives you a few things. First of all, it gives you just radiation shielding. So as I said, when your measurements are single atoms, you just want no radiation whatsoever. It's like anything will just wreck it. So it gives you, radiation shielding. It gives you a place to literally just like mount your PCB. In terms of structure, so there's these two PCBs here, which are literally just like prefab PCBs. And then the actual amplifiers sit on this little wafer of superconductor there, and you can just bond to it with gold wires. Yeah, whole thing. It's a lot. Yeah. So these quantum fridges, you basically set up your experiment and you screw in your SMAs and you put it in the fridge and you close it all up and you kind of pre-cool it with liquid nitrogen and then you chuck in your liquid helium and you basically just hit on, leave it for about 72 hours, go home, come back on Monday, and then the thing's cold and then you can do your measurements. And so you've got to make sure that everything gets plugged in because it's a real slow process cooling it down.
Using Peltier effect when you get right down to the end?
Yeah, so it depends how cold you need to get it, but for 1 millikelvin, for 1 Kelvin, you can basically just dunk it in liquid helium. So liquid helium is liquid at 4 degrees Kelvin. So if you just have a bath of liquid helium, you can just chuck it in it, you get 4 degrees Kelvin for free. If you want to get to about 1 degree Kelvin, you can, if you get liquid helium and you pump a vacuum on it, it'll drop down to 1 degree Kelvin. In the same way that the analogy that's often used is kind of like blowing a cup of coffee, where if you've got a liquid that's at 4 degrees Kelvin, it doesn't mean that every atom in there is at 4 degrees Kelvin. It basically means the average energy of those atoms is 4 degrees Kelvin. And so if you pump a vacuum on it, you take away, so you got your liquid, you pump away all the gas, and the most energetic, so the hottest atoms will evaporate. And if you pull those off, if you pull off all the hot ones, the average goes down. Correct, 100%. And it's the same reason why blowing on a cup of coffee cools it down, is because if you got a cup of coffee, every time a molecule gets to 100 degrees Celsius, it'll get liberated into the gas phase, right? It'll boil. And if you just chuck the lid on your cup of coffee, it'll boil and boil and boil until the pressure of kind of the atoms trying to get out of liquid matches the gas pressure. But if you blow in it, you destroy that equilibrium, and so more of the high energy molecules can come out. So yeah, basically you get a tub of liquid helium and you pump on it, and it cools down to about 1 degree Kelvin. To get to the millikelvin temperatures, you use quantum mechanics. And so there's some real cool stuff you can do where you basically get helium-4, which is one isotope of helium. You chuck a layer of helium-3 on it, and you can use fancy mechanics, which I'm happy to chat to you about. It's really interesting. But you can use that to more or less get down to absolute zero, basically. Yeah, it's real cool, pun intended. But yeah, so this is, yep, I made a box. The point of that. And the reason there's 2 through holes here is there's 2 mounting points, so it'll support either a large, like a long structure, or if you want a real small structure, you can just slide it together, and there'll be a second set of mounting holes, so it works for that. Yeah, it's true. But I actually, when I went to Fusion 360, instead of using the shiny copper setting, I used the brush copper setting, so it makes it more realistic. So this is for like the traveling wave structure. As you can see, there's a 2-port device. I also made a 1-port version, this is without the PCB, but it's basically the same thing cut in half. The other thing I did is I did a lot of design and simulation of these structures there's a great RF simulation tool called Sonnet. The reason we use Sonnet is because it was the only one we could find that actually simulated this kinetic inductance thing. And so you kind of draw your structure, and then you just click on it and say, I want your surface inductance to be blah. And so it's the reason we have to use this. It's actually very, very powerful. So there's lots of simulations in that. Another thing I had to do was when you actually design these things, when you actually build them, you put them in what's called an EBL machine, which is electron beam lithography, which is a fancy way of saying you put down your material and you just kind of shoot electrons at it and etch away your material, and that's how you build these things. And the way you get these EBL machines to work is you draw the structure. It's kind of like a fancy printer. You draw your structure and it etches it away. And yeah, these structures are really, really fine, and so it's really slow to kind of go through and draw them by hand, even with copy and paste. And so I did a lot of Python scripting to actually design these structures. So this is an example of some of the output I was doing. So so this is to be etched away. So you've got ground, you've got your center pad there. And then so this is your transmission line. If you zoom in, that's what it looks like. So you've got your center conductor, but you can see how fine this structure is. So lots of, as I said, Python scripting to actually you give it a whole bunch of parameters. So you say, I want, 8 meanders, and I want it to be this thick, and I want the loads to be this far apart, bang, and it just spits out one of these GDS files, which is good because it makes it really dynamic and flexible. So you design a structure and you go, I want it to, amplify at 7 gigahertz, and you print, and it'll amplify at 8 or something. And so it speeds up the process of actually designing these things, where you can change one parameter and the whole thing gets redesigned. And this is the finest of the structure. You've got this center conductor, and you've got these loadings, and you've got like a ground spacing. And it's a really fun problem if you like maths and like mind-bending things, how you do this computationally, because what you're defining is like you've got a center conductor, you've got a center line, and then about that center line you've got these 2 kind of meandering structures. So if you want a mind-bending thing, just thinking about how you actually define those geometrically, it's just a fun little, I don't know. I'm an engineer, I find these things interesting. But the last thing, and where a lot of my time was spent, was actually creating a design tool that designed these Bragg resonators. When they're designing these structures at the moment, it's not, to say guess and check would be to put it far too simply, but essentially what they need to do is each of these sections, so the resonator and the low impedance section, the high impedance section, kind of build a section of it, measure its dielectric constant, measure its characteristic impedance, string a whole bunch together. And it's this sort of quite slow iterative process where you need to simulate it in parts and actually etch it and test it. And so what I did is I made another Python script. Have had a fair bit of experience in programming. So I wrote another Python script that you could just say what you wanted. So you say, I want a Bragg resonator that will resonate at 8.48 gigahertz with a quality factor of 5,000. Give it to me. And it will just spit out the geometry of this thing. So it'll say, well, if you make a thing that's this long and this thick and on this material and stuff, then it will work. And so the goal is for that to really speed up the pace of research, to allow people to simulate these things. If you're interested, this is kind of the approach that I took. You've got a whole bunch of knobs that you're trying to choose. So you've got the number of cells, you've got the length of your resonator, you've got the length of the low and the high impedance section. And then it's also all a coplanar waveguide. So if you slice it sideways, you've also got like the thickness of the dielectric constant, the thickness of the conductor, the center width, and the width of the gap. So this is why it's really important to do this thing computationally, because you have lots of knobs. But the kind of approach that I took is you can use some quite cool calculations to simulate the impedances of each of these sections, and then you string them together. You calculate the ABCD matrices of each of these sections. You multiply them together, and then you take the S11, and it'll actually give you the resonant properties of that. And then you can use like a gradient descent method. So you say, my quality factor is here, but I want it here. And so you can increase your lengths, and you get this iterative generation. And this is just some big maths to scare you. But what this is how in industry, and this is from a paper, this is by no means my own work, how they actually take the geometries of a coplanar waveguide and simulate the dielectric constant and the characteristic impedance. And to give you an idea, this is sort of the accuracy of the numbers that were coming out. So this is the dielectric constant, the impedance as simulated in Sonnet, these RF simulation tools, and these were the numbers that were coming out of the simulator. And you can see they're like basically bang on, good old X equals Y. And then, so these are the numbers that finally came out at the end. So you can see these are all built on silicon. There was a target frequency. So in the left column, that was the target frequency, and then a target quality factor that they wanted to be designed for. And then I put these into my design tool and said, produce me a structure. And these were the actual values that came out. So you can see they're close-ish. So if you're simulating, you want 7.25 gigahertz resonant frequency, it would design a structure that had a resonant frequency of 6.9, which I realize in the radio communication space is a large margin of error. But the great thing about these research tools is you can actually just, you give it like a ballpark frequency that you want to measure at, and you can actually, using magnetic fields, just tune into it. So the point is, this is really useful and it works. So I'm really happy about that. Yeah, so that's basically my my contributions. As I said, I hope that didn't go over too many of your heads. It's some really cool stuff, and I spent a fair bit of time thinking about it. But if you have any questions, I'd love to hang around and chat to you. And also, I wouldn't be a good student or an engineer if I didn't give credit to all these fantastic people in papers and Google Images who provided this information. So thank you so much for your attention.